Thank you, Valentine, for inviting me. This is my pleasure indeed. Again, this is my talk. It's about the futuristic electric energy paradigm. Before starting the presentation, thank you all for attending this presentation. Hopeful all of you are safe and in good health. And good morning to everyone in the US, and good afternoon or evening away from the US. So this talk is to give a certain view about the future of the electric grid. First of all, I appreciate, of course, the help of Dr. Shadi Khalil, Sertaj Bayan, and Mohammed Shadman for helping me and putting the slides together, preparing many of the slides. The outline is to introduce the topic, talk about this future grid paradigm, microgrid stability of the power electronics, dominated grid, microgrid protection, little about the situational awareness, cybersecurity issues, and then I will conclude the topic. Well, so this is a view of the traditional grid structure, which is, I would say, the best ever engineering invention. However, currently is not able to fully respond to the growing humanity needs and expectations. This structure, this paradigm has over 130 years and is characterized with large generation stations, centralized control, unidirectional power and communication flow, limited interaction with loads, reactive maintenance. So this grid actually, this infrastructure is overstrained and it cannot fully support the integration of renewable energies. Speaking about a huge amount of renewable energies with various natures, characteristics. So fluctuating quality of power and the reliability are the major constraints in this our current paradigm. And this is, of course, is very evident speaking in the US. So you speak about tens or even more $100 billions as a cost of power disturbances across all the business sectors. Of course, speak here about the result of outages. In addition, of course, to the power quality phenomena aspects. Well, so this means that our current grid should be transformed to create next electric energy paradigm. And this new energy paradigm should be flexible, accessible to all types, of course, and amounts of those renewable energies, reliable, and able to respond to all pressing needs and expectations of our generation and the next generation. Our current grid, the existing network, is already being transformed, but mostly by increasing the penetration level of renewable energies. This slide, as we see, shows how the example of wind renewable energy in Europe is overtaking all other traditional generations over time. The solar energy, the same actually, or even more, because PV renewable energies is showing the highest amount, highest increasing rate of installations worldwide, everywhere this is noticed, which means that the future is full of renewable energies. This slide actually shows renewable energy share from 2017 and the target in 2050 by a few countries. As we see here, some of the countries, including Denmark, they are targeting 100% renewable energy grid paradigm. Other countries, 80% and more. But of course, this is an indication of the denomination of this renewable energy in the next energy paradigm. But all those renewable energies are actually power electronics based. So those are controlled and managed using power electronic converters. In other words, the next grid paradigm is transforming this, our current energy network, of course, grid, from the high inertia synchronous machines to fast responding power electronics based. So low inertia to high inertia to low inertia. So all this, of course, creates the low inertia system, the so-called grid, power electronics dominated grid. So the question now is how this network will behave when moved from synchronous generation based to this power electronics generation based. So synchronous generator with large inertia, it is actually clear known that it maintains the synchronism and prevents grid collapse or blackout. So the high inertia power system with synchronous generators, our grid, has a robust frequency. And it is frequency deviation and the rate of change of a frequency can easily satisfy the grid requirement. But now when we actually move to the next energy paradigm, the power electronics dominated grid, now the inverters have very fast response and lack of inertia support for damping adjustment ability. So therefore, such grid's ability to suppress those fluctuations, disturbances, is weak. Fortunately, the transition from this bulk power system to the next power electronics dominated grid paradigm will not happen at once. So smooth transformation to the new energy paradigm can be achieved by modularizing this grid into multiple sub-control, sub-management regions, such as the microgrids. Makes things easier to manage. So building a grid of microgrids could be a promising solution to create this futuristic, smart electric energy paradigm. So we speak here about the so-called microgrid, which is defined as a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid and can connect and can disconnect from the grid to enable it to operate in grid connected or islanded modes. So it has many advantages, such as increasing the grid's reliability, security, possibility to incorporate large amount of renewable energies, improving the efficiency, voltage quality, providing uninterrupted power supply for, let us say, critical infrastructure. Microgrids installation has become a very high focus worldwide and interest. So here you see the number of installed microgrids has been growing over time, sharply growing over time, particularly during the last few years. The data is showing over 20% annual rate increase of the installation. So speaking now about tens of gigawatts installed microgrids. We have AC microgrids, we have DC microgrids, we have a combination of both. So AC microgrids are easily integrated to our conventional AC grid because most of loads in our life and the grid itself are AC. So although the most of those installations are AC, but number of DC microgrids has been growing very, very sharply actually. So you speak here about more a rate increase of DC microgrids as installations than the AC microgrids, but as a number, not as a capacity. So if we compare now with AC microgrids, so the DC microgrids are simpler structure, lower cost. They may provide better power capability with higher efficiency, higher reliability, lower cost, easier integration of many renewable energies. Now, DC microgrids, unfortunately, still they need more research efforts. The AC, actually, the AC environment, infrastructure are so mature. So moving to the DC requires a lot of standardization, control, protection, so a lot still to do. If we move to the hybrid, this is kind of hybridizing both DC and AC microgrids so that you combine the advantages of both. So also those are available, such kind of architecture. All those microgrids actually integration with the renewable energies, etc. Those are built, those are designed using power electronics converters. So we speak here about so-called grid forming power converters. You need to build this microgrid. So those converters can be represented as controlled voltage source. So the converters do operate in islanded mode. The other one, the so-called grid feeding power converter, which can be presented as controlled current source. And these converters are suitable like to operate in grid connected mode. And another one of those converters is the so-called grid supporting converter. So this kind of topology combines the advantages of grid forming and the grid feeding converters. So it can operate in islanded mode or in grid connected mode. So such kind of converter, of course, do support the grid in order to keep frequency, to give the voltage close to their rated value. So those are grid supporting converters. As we see here, during a grid connected mode, the inverters need to behave like a current source, regulating the output power. And during islanded mode, those inverters need to behave like voltage sources, regulating the output voltage, and of course sharing the power with other sources that are connected in parallel. Again, so this question now, when you have this futuristic grid, so power electronics domination. So can those power electronics converter play the role of machines exciter, similar to the synchronous machines? Can they be controlled to behave the same way as the governors and support system frequency? So while having such kind of a grid, so those grid connected inverters in this low inertia power system are also, of course, required to provide additional frequency response function, similar to the synchronous generator, of course, by various strategies, such as well-known and simple droop control. So droop control, power frequency, active power frequency, reactive power voltage. It is very well known. The droop automatically adapts the changes, whatever changes in the load, by changing the system frequency and voltage according to the load demand. So droop control strategies, those allow the microgrids to operate between two modes of operation, grid connected and islanded mode. Advantages such as higher reliability, they don't need communication, flexibility, plug and play feature, connecting and removing the DGs is easy and easy to be implemented. They have disadvantages such as voltage frequency deviations in the islanded mode, and of course need central synchronization control so that could be connected, reconnected to the grid. Well, modification of the group is to operate the power electronics converters as so-called virtual synchronous machine to mimic the behavior of the synchronous machine, the characteristics of synchronous machine. So those DGs behave like a synchronous generator connected to our traditional system. So they have the power balancing ability that could be emulated. Well, so what we have is a virtual synchronous, so-called virtual synchronous machine is designed based on emulating the mechanical and electrical equations, of course, of the synchronous generator to control this grid-connected inverter. And such controller consists of the electromechanical block that emulates the inertia and another virtual admittance block that emulates the electrical characteristic of the synchronous generator. Then you control the active power, reactive power, and share it among the DGs. Well, now also it is possible to enhance the inertia of the DC microgrid that has very low inertia, of course, by introducing the virtual inertia control into the bidirectional connected converter, which is similar the same way to the virtual synchronous machine. So in this way, so you have the reference current compared with the measured, and then you can control the DC bus voltage and having the droop coefficient and behaving similar to the virtual synchronous machine related now to the DC microgrid. So if we compare actually the characteristics between those AC and DC microgrids, the AC with the virtual synchronous machine, DC with the bidirectional grid connected converter. So now when the frequency of an AC microgrid starts suffering from certain disturbance, then the rotor will quickly provide active power support. On other side, now when the DC bus of the DC microgrid suffers from disturbance, then the capacitors can quickly provide this active power support. This slide shows an improved droop control with the frequency and voltage restoration and virtual impedance, so that could enhance, of course, the response of the system. And it works for like different line distances. So the active power, reactive power could be controlled. And you have the inner control loop controlling the voltage and the current. And the system actually, the power is shared among 3 generators, while the voltage and the frequency are stored at within the limit. This is a simple simulation for an islanded mode control. So we have islanded mode. The microgrid here, it has 2 DGs. So the load is 20, and the 2 DGs, they have the same droop. So they equally share the power, 10 plus 10. Reactive power 0, and here reactive power is added to be 5 kilobar. And the power is increased from 20 kilowatt to 30 kilowatt. Again, they share the active and reactive power. The grid power is 0. And again, here is moved again the load to change to 20 kilowatt and the Q to 0. So the system behaves smoothly during all operating points. This is the situation when it is grid connected. The load is 30 kilowatt. One DG is 20, the other is 27, generating 27.5. So in total, so they are supplying the load, and 17.5 kilowatt is injected to the grid. Another example here, the grid connected mode, in which first the load was 50 kilowatt. One DG is 20, the other is 30 kilowatt, and they share the load. No power now goes, because 20 plus 20 is 50. No power is injected to the grid. At this instant, the load is increased to 100. So 50 kilowatt is taken from the grid at this instant. Here is the transition between islanded to grid connected mode. At this instant, 40 kilowatt, 20 DG1, DG2, supplying the full load. So no grid power at this instant is connected to the grid, and DG1 is supplying 20 kilowatt, DG2 30 kilowatt. So the load is 40, and 10 now is injected to the grid. Well, so what we have here, this is the so-called hierarchical control. So what's that? We should have a proper microgrid control for regulating the voltage, frequency, of course, controlling active and reactive power, achieving this kind of seamless transition between grid connected and islanded mode, participating in grid black start in case of any failure, enabling ancillary services to the grid. So such kind of things could be achieved by this kind of combination, the so-called hierarchical control structure. What's that? So it has a field level control, so-called primary control, and the so-called power quality control, the secondary, and the economic control, the tertiary. Well, so this is the primary control. This is the device level. This is the field control level. Of course, this is the controls the power electronics converters operation. Then you go to the secondary one. So voltage and frequency control, restoration. So this corrects the system level deviations, provides active power and reactive power to the references, of course, to the primary control. And then you go to the economic level, the tertiary control. And this is in the case of a grid connected is used. Regulates the energy exchange with the grid, and of course connected with other microgrids, ensure maintaining grid regulation, achieving high level technical economic objectives. Well, so now this, of course, seamless transition is very important here. So seamless transition between a grid connected and islanded mode is a key in the success of this grid paradigm. So the whole control with very smooth connecting and disconnecting from the grid. In total, we have three major categories of the control. So we have the decentralized, we have the centralized, and we have the distributed control schemes. So the decentralized, this one, mostly this decentralized is group-based. Such schemes provide proportional active reactive power sharing. They do not require dedicated communication. The other one, the centralized, that require dedicated communication, distributes the control into 3 layers, could be primary, secondary, and tertiary when working across the grid, connecting many of the microgrids as well. So each control layer, of course, is responsible for a specific task. A combination is the distributed scheme. So this kind of a scheme combines the advantages of decentralized and centralized control schemes. So those require, of course, local peer-to-peer connections that could be, of course, realized using the available communication links. To compare this slide, kind of comparison between those control schemes in terms of course, synchronization, dependency, synchronization, time, power quality, communication, dependency, power sharing, controller configurations. The distributed control scheme could be a compromise in terms of advantages. Okay, so there are many open research, of course, questions that are focused on moving the functionality of this bulk power system to the grid edge with thousands or even millions of inverters that are working in different operating modes. So important point here is the penetration level of power electronics-based generation, but without jeopardizing this power grid stability. So stability of such a grid is very, very important. To understand this stability challenges of this power electronics dominated grid, let us make a look at this hanging pendulums such network, which represents the inertia, those two, the inertia comparison between the bulk power system and the power electronics dominated grid. This is the traditional grid, which is represented by heavy pendulums, large synchronous machines. So those are in certain stable equilibrium point. Now, if there is a disturbance occurring, it will impact one of those, let us say, impacting one of those pendulums, then a significant number of other pendulums will start to oscillate, but eventually will reach an equilibrium. Of course, because those pendulums are heavy, so traditional power system, this bulk power generation system, such oscillations are damped quickly. But now if we go to the other case with the same scenario, considering the light pendulums, those light pendulums represent low inertia power electronics dominated network. Then major oscillations will occur that will take longer time to damp. Of course, this indicates that the possibility to reach an unstable equilibrium is higher, much higher, in the case of power electronics dominated grid compared to the bulk power system, of course, given the same size of disturbances. Again, this figure demonstrates the comparison between synchronous generator-based system and power electronics dominated grid, of course, regarding the degree of coupling now between active power demand, reactive power demand, frequency, and voltage, of course, by analogy to the weighing instrument. Now, in the case of synchronous generator-based power system, the balance between active power demand supply impacts only the frequency, while reactive power demand supply impacts only the voltage. But if we move now to the power electronics dominated grid, active power demand supply, this balance is coupled with both frequency and voltage. The same reactive power demand supply balance is also coupled with both voltage and frequency. This, of course, means that any instability in the PEDG, power electronics dominated grid, of course, will result in oscillations in all those variables. Therefore, most logical categorization of this instability in this power electronics dominated grid to be the origin of instability. Speaking here about supply and demand stability, and control stability. So this slide shows the power electronics dominated grid stability categorization, of course, with root and the resulting phenomena. Now, while the supply demand stability covers, as we see, voltage stability and frequency stability. The control stability, of course, it includes the power converters control and the machine control. This slide, again, table, shows now the origin of instabilities with their effects on the network parameters. So, of course, it shows that instabilities have such effects like huge power and frequency variations, large rate of change of a frequency, huge DC link voltage fluctuation, injection of undamped low frequency power and voltage oscillations into the grid, steady state voltage oscillations, aperiodic voltage and frequency variations, etc. So there is a lot of open research on stability challenges in this power electronics dominated grid, of course, in comparison to the power bulk, this bulk power system stability. So questions like open research, open point, how the angle stability will be impacted with mixture of converters and conventional those synchronous generators at different various levels. How the power converters terminal voltage, DC link voltage, those fast controllers contribute to the voltage dynamic stability. Means at what level they can play the role of machines exciters, at what level. What is the impact of moving the voltage control from generation side into this bulk power system to now speaking about thousands or even millions of inverters at the distribution level, and how they can will impact the voltage stability in this power electronics dominated grid. How much this new generation paradigm can behave the same way as governors and can support the system frequency. What will happen to the long-term frequency regulation issues? For example, how optimal energy dispatch and unit commitment problems will be solved or should be solved. Another issue is protection. So microgrid protection is a big challenge because it's not an easy to design such protection system that responds to both mini grid and microgrid faults. Some of those challenges are the fault. Of course, fault current magnitude can be very high and can be very low, depending on the operation mode. Grid connected very high, islanded very low. Inverters have low fault current contribution, so it would be difficult to distinguish between load and fault current. There are many DGs in the microgrid, which result in a bidirectional fault current flow. The current protection is not prepared well for solving those aspects, challenges. So it is important for the microgrids to have flexible protection schemes that can operate in both grid connected mode as well as islanded mode. It's important to have adaptive protection methods and effective islanding protection, relaxing ride-through requirements. This shows the relaxation of the rate of change of the frequency. So actually, With increased penetration level of those renewable energy sources, generation units have to survive severe rate of change of frequency following, of course, a major generation loss, rather than tripping those generation units and causing cascading. So therefore, certain specific rate of change of frequency right through such requirements are introduced in some of the grid codes. Typical rate of change of frequency relays for the 50 Hertz system between 0.1 Hertz per second and 1 Hertz per second. So some countries, like you see here, have already relaxed the rate of change of a frequency. Of course, those did it to meet the penetration target in 2020, by this year. As you see, it's a lot of relaxation that which is good. Again, so we have AC microgrids and we have DC microgrids. So kind of comparison from this protection point of view, most available protection methods are designed for AC. Cleaning faults is performed in the AC system using or at zero crossing point. Some standards are available for the AC microgrid protection. In the DC microgrid, the problem is bigger. So we speak about due to those differences between the nature, of course, of DC and AC system. AC protection cannot be just applied to the DC system. So we have in the DC microgrid very high rise of the fault current. There is no zero crossing point. So clearing the fault in the DC circuit is very challenging, and lack of standards for the DC microgrid protection. Well, last point, I would like to talk briefly about the situational awareness and the role of this energy paradigm in enhancing the system performance, system security. This futuristic power electronics dominated grid paradigm is coming as part of the smart grid paradigm. So the smart grid at larger description is associated with the flow of huge amount of data and utilization of data from different, of course, sources, different meters, sensors, smart units, smart converters, of course, speaking, smart transformers, etc. So those smart converters are expected to generate and transmit a huge amount of important data, and even play the role of PMUs. So flow, of course, of data makes the system more and more vulnerable to the various attacks. So it has big advantage, and now it's very important to solve this advantage, those challenges or problems. So if now power electronics converters are optimally utilized, they can play an essential role now in strengthening the resiliency of the whole futuristic grid, from the lower level to the very high level. Of course, such smart converter can assist in detection and protection at the physical layer against, of course, various anomalies, coordinated and non-coordinated, with the self-healing feature, intelligent units. So each smart converter, of course, would have its own intelligence and would observe its own situation and the neighboring units as well. Such smart inverters, of course, in case of an attack, in case of fluctuation in the grid, they can cooperate together harmoniously. They can mitigate the problem. They can provide resilient solutions, help support for the critical infrastructure. Of course, this should be achieved by creating such kind of smart, self-learning, self-healing unit and system. So smart inverter and the cluster that could be built, smaller cluster, larger cluster, at the microgrid, at smaller scales. Those should ban the data propagation from any compromised area at the unit level, at the cluster level, to the rest, of course, of units and to the rest of the utility, of course, to prevent against false data injection. So within the suspicious grid cluster, if there is a suspicion, so compromised smaller areas could be identified, of course, by comparing the measured and projected data that are obtained from such aggregate reference models. And then smart inverters under the cluster can, of course, be then investigated using let us say machine learning tools to verify compromised devices that could go for self-healing and then reconnecting when are cleared. As a conclusion, of course, the next grid energy paradigm, the next grid paradigm is I would say microgrid based, and in particular power electronics dominated grid based. So such heterogeneous nature of this grid, of course, results in unexpected events that may cause many problems, such as synchronization failures, instability, blackouts at various sizes. Therefore, there are many challenges that will be faced in the way to create this kind of smart energy paradigm, power electronics based. Some of those are controllability, stability, optimality, scalability, cybersecurity, and verifiability. Yes, this is doable with the support particularly speaking from the government, all around it, local authorities, operators, etc. Proper standardization, legislations, focused mission-oriented research and development, of course, awareness of the opportunities, acceptance at different levels, ability of the users, building human resources, and clear national, global roadmap. This is kind of some of the recommended, such recommended references that you can get more information about the raised topic. With that, I thank you, and please, any question.